Welcome all. Here we are going to discuss about acid-base concepts. So, first is the theories of acids and bases. The first one is Arrhenius Theory of acids and bases. In this theory, an acid is a hydrogen-containing compound which, when dissolved in water, releases H plus ions, whereas a base is a hydroxyl compound which releases OH minus ions in aqueous solution. So, according to this theory, HCl is an acid and NaOH is a base. How can we illustrate this? HCl gives H plus and Cl minus in aqueous solution, and NaOH gives Na plus and OH minus in aqueous solution. Okay, so according to this theory, that is Arrhenius theory, acid is an hydrogen containing compound which, when dissolved in water, releases H plus ions, and base is a hydroxyl compound which releases OH minus ions in aqueous solution. Okay. So, according to this theory, the process of neutralization between an acid and a base is a combination of H plus and OH minus ions to form water. Okay. That is, H plus plus OH minus ions in aqueous solution gives H2o. This is the neutralization reaction or combination of H plus and OH minus ions to form water. Okay. So, the approximate constant C, that is minus 57 kJ, observed in the molar enthalpy of neutralization of strong acids with strong bases can thus be explained on the basis of the theory. Acids and bases which are almost completely dissolved in aqueous medium and thereby readily yield respectively H plus ions and OH minus ions are termed strong. So, strong acid or strong bases are those which get completely dissociated in aqueous medium and will yield H plus ions and OH minus ions respectively. That is, H plus ions from acids and OH minus ions from bases. Okay, in short, strong acids and bases are strong electrolytes. For example, strong acids HClO4, HCl, HBr, Hi, HNO3, H2SO4, etc. Strong bases are NaOH, KOH, CaOH twice, BaOH twice, etc. So these will completely get dissociated in aqueous medium. Acids and also bases. Okay, acids will produce or acids will yield H plus ions and bases will yield OH minus ions in aqueous solution. Acids and bases which are not completely dissociated in aqueous medium and thereby do not readily yield respectively H plus ions and OH minus ions are termed weak acids or weak bases. Okay, so weak bases or weak acids are those which do not completely get dissociated in aqueous medium. Okay, in short, weak acids and bases are weak electrolytes. For example, for weak acids, CH3COH, H3BO3, HCN, etc. Weak bases are NH4OH, C6H5NH2, etc. Okay, so these are weak bases and weak acids. Next is limitations of Arrhenius theory. Here, Arrhenius theory of acids and bases is too limited to encompass all compounds which exhibit acidic and basic behavior. It is because there are some bases which do not contain OH minus ion. Okay, so they are also bases, but they do not contain OH minus ions. The next is, it is applicable only to aqueous solutions. It is because it cannot account for the fact that several substances show acidic or basic characteristics in non-aqueous media. Okay, not only in aqueous solutions but also in non-aqueous solutions, some substances will show acidic and basic behavior. Okay, so these are the limitations of Arrhenius theory. Next theory of acid-base concept is Lowry-Bronstead theory. Okay, so according to this theory, according to Lowry-Bronstead theory, an acid is a substance which has a tendency to donate a proton to any other substance, and base is a substance which has a tendency to accept a proton from any other substance. Okay, so acid is a proton donor and base is a proton acceptor according to this Lowry-Bronstead theory. So what is acid? Acid is a substance which has a tendency to donate a proton to any other substance, and base is a substance which has a tendency to accept a proton from any other substance. The entity produced when acid gives up a proton has a tendency to regain the proton. Okay, so the entity produced after giving up the proton from an acid behaves as a base. So it is called the conjugate base of the parent acid. Similarly, the entity produced when a base accepts a proton has a tendency to donate the proton. So it behaves as an acid. It is called the conjugate acid of the parent base. An acid and base may therefore be defined by the general equation as acid gives H plus base. Okay. So from these we can conclude that an acid and a base which differ from each other by a proton are said to form a conjugate pair. Okay. It follows from the Bronstead-Lowry theory that in order for a species to behave as an acid, a proton acceptor, a base, must be present. Similarly, for a species to behave as a base, a proton donor, an acid, must be present. Further, when a species donates a proton, its conjugate base is formed, and when a species accepts a proton, its conjugate acid is formed. Okay, so when we see this equation, that is acid 1 plus base 2 gives base 1 plus acid 2. This base 1 is coming from this acid 1. When acid 1 donates a proton, it will become base 1, and when base 2 accepts the proton from acid 1, will become acid 2. Okay, or it can be represented as Ha plus B gives A minus, that is Ha donates a proton H plus to base B. Okay, so Ha become A minus and the base B become Hb plus. It is accepting a proton from the acid Ha. Okay, so acid 1 and base 1 constitute a conjugate base acid base pair, while acid 2 and base 2 constitute another conjugate acid base pair. Okay. So, the examples of proton transfer equilibria in water. Consider the reaction between HCl and NH3. Here, acid is HCl and base is NH3. So, HCl is donating an H plus to base NH3 and acid is becoming a base, that is HCl becomes Cl minus. Okay, so base NH3 becomes, when accepting H plus from HCl, it will become NH4 plus. HCl donates a proton to NH3 which accepts it. Thus HCl acts as an acid while NH3 acts as a base. NH4 plus formed has a tendency to donate a proton and thus acts as an acid. Okay, so Cl minus formed from this HCl will have a tendency to accept a proton and hence acts as a base. Thus NH4 plus and Cl minus constitute the new acid and base formed. Okay. Cl minus constitute the conjugate base of HCl, whereas NH4 plus is the conjugate acid of NH3. So next is the ionization of acetic acid in water. Here we can see that acid is CH3COH, that is acetic acid. It is donating H plus to the base H2O. H2O is acting as a base here. So H plus is released from or donated by the acid CH3COH, and the base H2O accepts this proton to become H3O plus acid. Okay, so this CH3COH is becoming a base. CH3COO minus is the conjugate base of the acid CH3COH. So H3O plus is the conjugate acid of the base H2O. The parent base H2O. Okay. So the next is consider the ionization of HCl in water. Okay. Here HCl is the acid and H2O is acting as the base. So HCl donates one proton to the base H2O and HCl is becoming Cl minus as base and acid H3O plus is formed here. Okay. So Cl minus formed is the conjugate base of HCl and H3O plus formed is the conjugate acid of the base H2O. Then next is the reaction between NH3 and H2O. Here as H2O is acting as the acid, NH3 is the base. When acid, that is H2O, releases one proton to NH3, NH3 become NH4 plus, and it is acting as the conjugate acid of the base NH3, and H2O when release H plus, it will become OH minus. It will have a tendency to accept a proton, that is it is the conjugate base of the acid H2O. Okay. So these are the other examples for the proton transfer equilibria in water. Okay, illustrating the acids like HNO3, H2SO4, HSO4 minus, H2CO3, NH4 plus, NH2 minus, and NH2 minus and HS minus are the base acting as the base in aqueous media. So these are other examples for proton transfer equilibria in water. Okay. Here are some examples for conjugate acid-base pairs. Conjugate acid, for example, HF, its conjugate base is F minus, and that for if the conjugate base is NH3 and its conjugate acid is NH4 plus. If the conjugate acid is HNO3, then its conjugate base is NO3 minus, and so on. Okay. So next is hydronium ion. When water accepts a proton from an acid, the former is converted into a hydronium ion, that is H3O plus. In an aqueous solution, a proton would exist in this hydrated form, that is H3O plus. This representation is too oversimplified because of the extensive hydrogen bonding further possible. The actual species thus would be H3O plus, H9O4 plus, etc. This is because there is extensive hydrogen bonding present in water. So H3O plus is the oversimplification of the representation of hydronium ion or hydrated form. Okay, depending upon the conditions such as temperature. For the sake of convenience, the formula H3O plus is used to denote the hydrated proton or hydronium ion. The next is amphoteric substances or amphiprotic substances. A substance which can act as an acid or acid base is called amphoteric substance or amphiprotic substance. So what is amphoteric substance? It can act as both acid and as a base. Okay. So the first example is water. What is a typical amphoteric substance? For example, it can act as a base with HCl and also an acid with a base like NH3. Here the reaction is given for the water acting as a base with HCl acid. We have already seen this equation. That is HCl is donating H plus to H2O and giving H3O plus as acid from the base H2O, and Cl minus is produced from HCl. Cl minus is the conjugate base of the acid HCl and H3O plus is the conjugate acid of the base H2O. The next is the reaction between NH3 and H2O. Here H2O is acting as the acid and donating H plus to NH3, the base, and NH3 is becoming NH4 plus, which has a tendency to donate a proton, that is an acid. It's a conjugate acid of the base NH3, and H2O is becoming OH minus, the base, which has a tendency to accept a proton. So OH minus is the conjugate base of the acid H2O. The next example for amphoteric substance or amphoteric substance is HCO3 minus. So this is the bicarbonate ion. It's an amphoteric substance. For example, it acts as a base with HCl and as an acid with NH3. Okay, so this is the reaction for HCO3 minus with HCl and with NH3. That is HCl plus HCO3 minus giving H2CO3 plus Cl minus. Here HCl is donating one proton to HCO3 minus and becoming Cl minus. and HCO3 minus is becoming H2CO3. That is, H2CO3 is the conjugate acid of HCO3 minus. And the next example is the reaction of HCO3 minus with NH3, ammonia. NH3 is accepting one proton from the acid HCO3 minus. So it is becoming NH4 plus, the conjugate acid of the base, parent base NH3. HCO3 minus is becoming CO3 2 minus, the base, the conjugate base of the acid HCO3 minus. Other examples are HS minus, HSO4 minus, H2PO4 minus, okay, etc. Are the examples for amphoteric substances or amphoteric species. So the relative strengths of acids and bases. Here, according to Lowry Bronstead concept, the strength of an acid depends upon the tendency to donate a proton. Okay. So consider the reaction or ionization of HCl in water. Here we can see that the equilibrium is more shifted towards left. That is, HCl is having a high tendency to donate H plus to the base H2O. That is why the equilibrium is lies very much to the right. On the other hand, Cl minus is having a very small tendency to accept a proton. So the tendency being much smaller than even that of H2O. HCl is a strong acid while its conjugate base Cl minus is a weak base. Then now consider the ionization of acetic acid in water. Here we can see that the equilibrium shifts more towards left. That is, CH3COH has only a small tendency to donate a proton compared to that of H3O+. So CH3COO minus is having high tendency or strong tendency to accept a proton. The tendency being much greater than that of the H2O. So CH3COH is a weak acid and its conjugate base CH3COO minus is a strong base. Okay. Examples of proton transfer equilibria in other protonic solvents. Okay. Ionization in liquid ammonia. On account of the strong basic character, liquid ammonia, even weak acids like acetic acid ionize to a considerable extent in liquid ammonia and thereby behave as strong acids. Okay. This is because liquid ammonia is having high proton accepting tendency. So the weak acids like CH3COH, acetic acid, ionize to a considerable extent in this liquid ammonia and behave as strong acid. Other one is ionization in anhydrous HF. HF is a strong acid, that is, it is having high proton donating character. So certain acids which show strongly acidic character in water, for example nitric acid, show weakly basic character in HF, anhydrous HF. This is because HF is having a high proton donating character. So strongly acidic character showing NH3 like acids in water will show weakly basic properties in anhydrous HF. And weaker acids like acetic acid show relatively stronger basic character in anhydrous HF. Okay. Here's the reaction of HNO3 in HF media, that is anhydrous HF. It is the solvent here. So an HNO3 when treated in aqueous solution, we know that it is a strong acid, but in this case it is acting as the base. So HNO3 is having a tendency to accept a proton from this HF and becomes H2NO3 plus an acid, and HF becomes F minus the base. Okay. In the case of acetic acid, that is CH3COH, it is having high tendency to accept proton because it is a weak acid in aqueous media. So in this anhydrous HF, it is having, that is CH3COH is having high tendency to accept a proton. So it acts as a strong base here. and it becomes CH3COO H2 plus, and it is the conjugate acid of CH3COH. Okay. The next is ionization in Glycial acetic acid. Substances like ammonia, which show weakly basic character in water, show stronger basic, that is proton accepting character in glacial acetic acid on account of the greater acidic character of acetic acid than water. We know that acetic acid is a weak acid, but when we compare its acidic character with water, it is having greater acidic character than that of water. So the substances like ammonia, which is showing weakly basic character in water, will show strong basic character in glacial acetic acid. Okay, the equation is reaction is shown here. CH3COH plus NH3 gives CH3CO minus plus NH4 plus. That is, NH3 is having strong basic character in glacial acetic acid. The next is advantages of Bronstead-Lowry concept and limitations of Lowry-Bronstead concept. First is advantages. The application of Lowry-Bronstead concept is not limited to aqueous solution. It is applicable to acid-base reactions in all protonic solvents including water. The concept defines specific species as acids and bases in terms of their proton donating and proton accepting tendencies, not in terms of ions they produce in aqueous solution. Okay, this is the limitation of the first one, that is Arrhenius theory. That is, Arrhenius theory deals only with this aqueous media. Okay, the ions produced in aqueous media. And the advantage of Bronstead-Lowry concept is that it defines specific species as acids and bases in terms of their proton donating and proton accepting tendencies, not in the terms of ions produced in aqueous solution. Okay, it is a concept much broader than that of Arrhenius concept, so it encompasses a wide variety of substances within acid-base category, including all Arrhenius acids and bases. Okay, so these are the three advantages of Bronstead-Lowry concept. Next is the limitations of Lowry-Bronstead concept. The concept places undue emphasis on proton transfer in acid-base reactions, whereas there are many which do not involve proton transfer. Okay, so here we emphasize mainly on proton transfer, and there are many other situations where there is no proton transfer. There is no involvement of proton transfer. Okay, even though they act as acid-base reactions. It cannot explain the several acid-base reactions that occur in non-protic or aprotic solvents such as liquid N2O4, SO2, COCl2, BRF3, etc. We have already said that the Lowry-Bronstead concept is mainly based on proton accepting and donating tendencies. So it cannot explain the reactions that occur in non-protic solvents like this N2O4, SO2, COCl2, BRF3, etc. Okay. So these are the two theories on acid-base concepts, that is Arrhenius and Lowry-Bronstead theory. Okay, thank you.